Dear students, today we are going to discuss about galvanic corrosion. The galvanic corrosion occurs when two dissimilar metals are connected electrically and they are then exposed to an environment. And when such a condition occurs, the metal which is present higher in electrochemical series undergoes corrosion, while the metal which is present below in the electrochemical series undergo oxidation. Now, the most common example of this type is zinc and copper. When they both are connected electrically, zinc being higher in the electrochemical series, having higher E0 ox, undergoes reduction. As you can see from this figure, the metal at anode is undergoing oxidation, and therefore, as you all know, that oxidation is basically a corrosion phenomena. So therefore, the metal which is at anode, which is acting as anode, always undergoes deterioration. While copper, which is present below in electrochemical series, having a lower E0 ox, undergoes reduction and behaves as a cathode. So the mechanism behind this: if the environment is acidic, in that case, during galvanic corrosion, hydrogen evolution will take place. While in case of neutral as well as alkaline solution or in alkaline environment, we have absorption of oxygen. This has already been discussed during wet corrosion, in which we have shown that under acidic environment, the electrons that are released during oxidation of metal at anode, these electrons are accepted by the H positive given by acid, and that H positive gets converted into H2, or you can say reduced into H2, and evolution of hydrogen gas takes place. While if the solution or the environment is neutral or alkaline, in that case, since there are no H positive, the electrons that are released by anode, as zinc in this case, these electrons are accepted by oxygen to form oxide radical, and these oxide radicals or hydroxide radical, and they form metal hydroxide or metal oxide, and in this way absorption of oxygen takes place. The example of galvanic corrosion is steel screws in brass marine structure, where steel containing iron is in contact with brass, which is copper and zinc alloy. Lead antimony, which is known as solder, that is used around copper wire. There also we have galvanic corrosion. Or steel propeller shaft in bronze bearing. Bronze is an alloy of copper, having copper and tin Sn. Steel pipes connected to copper plumbing. So these are the examples where galvanic corrosion occurs, and the same type of reaction takes place in case of galvanic cell, and therefore only the name galvanic is used. Now let us move on to the concentration cell corrosion. Concentration cell corrosion is a very important type of corrosion and very common type of corrosion. This type of corrosion occurs due to the electrochemical attack on the metal surface when the metal is exposed to varying concentration of electrolyte, or when the metal is exposed to varying aeration. Unlike the galvanic corrosion, concentration corrosion occurs in a single type of metal. As we have already discussed that in case of galvanic corrosion, galvanic corrosion occurs when two dissimilar metals are in electrical contact. While in case of concentration, a single metal rod can experience a concentration cell corrosion. When it is exposed to varying concentration, means when it is dipped in a solution or immersed in a solution where the concentration of electrolyte is not uniform, or when the air or concentration of oxygen is not uniform. This may cause local differences in metal ion concentration. Because of that, there are some local temperature differences, and we have a differential current generated in such a system. Most of the time, this condition or this type of corrosion occur when a metal rod or a metal structure is dipped in a liquid which is not properly agitated or mixed, because whenever mixing or agitation is taking place, the concentration of electrolyte or even oxygen is always uniform. But when a liquid is left without stirring, without agitation or mixing, then over a period of time the concentration changes. There is a gradient of concentration generated. At the bottom we have high concentration, and For example, in case of oxygen, the layer that is present at the top, since it is in contact with air, so we have higher concentration of oxygen. As we move deeper into the liquid, the concentration of oxygen is very less. Because of that, different oxygen concentration also, the metal experience concentration cell corrosion. Clear? So the part which experience poor oxygen, where limited supply of oxygen is there, for example, in case of a tank where a steel rod or iron rod is dipped, so at the bottom we have very little supply of oxygen, you have very little availability of oxygen. So in that case, due to the pure oxygenation, that part which is present at the bottom behaves as anode and start releasing electrons. These electrons travel through the rod and reaches to the point where oxygen is available in good quantity, and when it reaches where oxygen is present in good quantity, oxygen absorbs those electrons, so absorption of oxygen takes place, as we have when alkaline or neutral environment is there. You can see from this figure that a zinc rod is dipped in the solution of NaCl. Because of varying concentration due to non-mixing or non-stirring of this liquid, we have different concentration of Cl at different position, and therefore a differential current has been generated. Same is the case of iron pipe that are present beneath the earth crust. When they are laid down for some type of supply, these, due to poor supply of oxygen, they also start releasing electrons, undergoing oxidation, and therefore got deteriorated over a period of time. So this type of concentration cell corrosion or the differential aeration corrosion is very common and very, very important. Again, you can see the differential corrosion is corrosion of metal partially immersed or just below the water line. As I have already explained you, that if zinc rod is dipped in a solution partially and not agitated properly because of non-stirring of the solution, the area above waterline is strongly aerated while the area below waterline is poorly aerated, and because of that, the portion of the rod that is inside the solution behaves as anode, releases electron, and the oxygen which is present at the open end, which is above the water level, absorb those electrons, and in presence of water react with water also to form hydroxide ion, and that hydroxide ion reacts with zinc to form zinc hydroxide or metal hydroxide. In this way, the metal keeps on converting, the pure metal keeps on converting into the hydroxide or the corrosion product. In a similar way, we have corrosion of iron. For example, if a structure of iron or a rod of iron is kept in open, and during raining, after the raining, some of the portion of iron rod is being covered by the water droplet while some portion are open. The portion that are open are very good supply of oxygen, while the portion of iron rod that is below the droplet has been poorly aerated. Because of the poor supply of oxygen, the portion of iron rod which is below the surface of that water droplet behaves as anode and releases electron. So in this way, corrosion occurs during raining. There are some general facts also about differential aeration corrosion. The first is this corrosion is accelerated in inaccessible areas as these areas become anodic. Why? Because inaccessible areas which cannot be accessed easily, therefore such areas becomes poorly aerated, and since they become poorly aerated, they become anode, and when they become anode, they releases electron and undergoing oxidation or corrosion, because oxidation is the main phenomena in corrosion. Second point, the corrosion accelerated under dirt, sand or scale formation, because whenever some dirt or sand is being deposited or scale formation occur on the surface of metal, then that portion at which the dirt or sand is there or scale formation is there, that again becomes inaccessible, and when it becomes inaccessible, it will act as anode due to poor supply of oxygen. So these all factors that are making a metal surface or a region of metal surface inaccessible, they make it poorly aerated, and when it becomes poorly aerated, it start releasing electrons undergoing oxidation. Point 3. Metals exposed to aqueous environment corrode faster under blocks of wood, pieces of glass. For example, if a metal is dipped or if a metal is immersed in a liquid, so and due to, for example, most of the time in rivers and in ponds we have certain kind of waste material flowing, for example pieces of wood or pieces of glass or polythene, paper. If these pieces of wood, glass, polythene or paper got stick on the surface of metal, then that portion becomes inaccessible, and when it becomes inaccessible, it becomes poorly aerated, resulting into accelerated rates of corrosion and on that particular portion, on that particular region. So this was all about concentration cell corrosion or differential aeration corrosion. Now there is a very important phenomenon which is known as passivity. Passivity is defined as the phenomena by which a metal shows very high corrosion resistance than it is expected from its position in the electrochemical series, even that as resistance is not expected from its position in the electrochemical series. And this series shows that the highest level of passivity is being shown by TL, then we have Al, Cr, chromium, beryllium, then we have molybdenum, Mg, magnesium, nickel, cobalt, iron, manganese, zinc, cadmium, tin, lead and copper. So this is the series, while TL has the highest passivity, and they exhibit very high resistance in oxidizing environment. But in reducing environment or reducing solutions, they become chemically active. This shows that this passivity occurs because of the formation of the corrosion product. When they are present in an oxidizing environment, they react with oxygen and a corrosion layer is formed which is protective, and once that protective layer is formed, further corrosion stops and the metal starts showing very high or very exceptionally high corrosion resistance. But when reducing environment is there, no oxygen is there, they become chemically active and undergo corrosion. So this also shows that passivity or passivation is not a permanent phenomena. This is a phenomena that exists in certain environments only. For example, as I told you just now, that in oxidizing environment, because of free supply of oxygen, they react with it and they form a layer which protect the metal from corrosion, while in reducing environment this is not the case. So passivation is not always a constant property, and metal not always show passivation. It only show under certain environment due to the formation of a very protective corrosion product or very protective oxide film on its surface. So this is all about galvanic corrosion, concentration cell corrosion or differential aeration corrosion, and passivity. In the next lecture, we'll discuss some more types of corrosion on metal surfaces. Till then, thank you very much.